Like every country in the world, governments reorganize, relabel, consolidate. And what I'm saying is a personal title. So there is a new institute called Earth Science New Zealand, which last year you maybe remember it was NIWA. But this is a consolidation of one or two institutes. And I believe that they will tell you what is their mandate. But I will introduce, what are they?
Yeah, so Deidre and I are going to we're going to tag team this one. And it's nice that Nicholas had a little bit about, we have to say a little bit about who we are because we are brand new. You can see our very, very quickly designed logo, which I imagine will change this year when we get a new chief executive in 2 months' time. But basically, we're from Earth Sciences New Zealand. I think for our American colleagues, it'd be like you combined NOAA and USGS into one organisation. Or I'm thinking for the Australians, it might be like a combo of the CSIRO, Geoscience Australia and the Bureau of Met, all kind of mushed together. More people, more problems, but a very exciting time for us here in New Zealand. We are a combo of 4 different organisations. So our colleagues at GNS Science are all the solid earth geology types, so things like earthquakes, volcanoes, a little bit of groundwater stuff, resources, energy, a lot of those kind of things. NIWA, which is where Deidre and I are both from, we're also absorbing the Met Service, which is the national forecaster that'll be happening this year. And for good measure, we're picking up the Measurement Standards Lab, which I'm kind of quite excited about because there's a whole bunch of really interesting things they do, like time standards and measurements that are very cool and sort of relevant to a bunch of our quantum applications that we're starting to think about now. So that's who we are, and we have this really broad breadth of kind of impact that comes out. So I just wanted to share a few slides. Deidre's going to talk about the actual meaty technical bit of the talk. I just get to wave my hands about what we do. And I was thinking about kind of sovereign capability, and it's a little intimidating, I think, coming in here and listening to kind of, we've invested £800 million into massive AI clusters, sorry, Simon, or the big Japanese Zeta-scale machine. This sounds a long way from what we have here in New Zealand. But I think we still have really good impact. And so one of the things that we like to think about in terms of sovereign capability in New Zealand is really this breadth of technology. So I just wanted to give an example. It's a few years old now. But do folks know what this is? Yeah? So, Don? Team New Zealand. Yeah, we're very proud of Team New Zealand. So these are these amazing foiling boats that are out there. This is kind of the latest iteration of the America's Cup. And Sail GP, you might have seen that's been going on for a while here. Yeah, there's no engine. It's fully sail. It's all about using the environment. And what's really interesting about this is a lot of the technology that goes into this as well. So it's not just that we have a great team, Team New Zealand like the All Blacks. We're very proud of those guys. But there's actually a whole bunch of New Zealand technology, manufacturing, design, carbon fibre engineering, all of that kind of stuff that actually goes into the build of these boats. But what's really interesting, I guess, from our point of view is we put a lot of the environmental intelligence in behind their successful America's Cup defence on the Waitemata Harbour. So you can see that on the day, the skipper is responsible for putting the boat in the right place to get these amazing kind of races that we have going where seconds really matter. But in behind that is a whole bunch of information about what the environment is doing. And we were the forecaster for them. And actually, one of the things that we did, and I'm just going to see whether I can get both of these playing, was run some sort of ultra-high... Sorry?
Cross on the second one will play.
Oh, okay, sweet. I think they're both going now. I've got them working. So there we go. So one of the really cool things we were able to do for them was run an ultra-high resolution sort of coupled weather and ocean model for them. And so what you can see is this is effectively a 300-metre resolution model across Auckland. We've actually been running this since the America's Cup in 2001, so we now have a huge amount of really, really high-resolution data at an urban scale, which we're now starting to think, what do we do with some of our AI simulators? Some of the downscaling stuff that I think Karen was talking about earlier starts to get really interesting here. And in fact, if you're starting to think, if I'm Amazon and I'm wanting to punt packages from one side of Auckland to the other with drones and some of the stuff that DK was talking about earlier, this kind of data really starts to get really, really interesting. So we're sort of got this breadth. We like having this breadth because we have this wide range of impacts. Yes, we do forecasting for the nation and hazards, and Deidre will talk about that in a minute. But we also get to do these kind of fun projects where we work with people that you might not think about as sort of a national government organisation working with. And so I just want to finish. I know Nicholas has been whinging at me about how terrible the weather has been, and we've put the wrong numbers into our supercomputer. This is one of the renders from a couple of days ago. This is this big East Coast low that we all now know and love that has been hammering us for the last few days. And what you can see is the huge amounts of rainfall. We've had power outages in Wellington, and in fact my home down here in Banks Peninsula has had a wee bit of flooding as well. So this is kind of one of these events that's really sort of hammered quite a few areas of New Zealand, and we seem to be getting these, about once every year or so. The reason I just wanted to show this was to sort of relate it back to Karen's talk about stability and that the physics matters. This has been a really interesting event because my HPC team were up till 2 a.m. in the morning trying to stabilise all our weather models, because the observations we were getting off our network were generating such large corrections to the models that actually they were becoming unstable. So we're starting to see sort of some of these big models having effects. The physical models aren't always perfect. These kind of stability questions really come into the way that we operate things. And obviously, I guess for New Zealand, these have some sort of impacts in terms of the advice that we can give. So with that, I'm going to hand over to Deidre, who does a lot of the actual thinking rather than the hand waving. And we're going to look at a little bit more detail in how we go from something like this to keeping people safe in a flood. Deidre.
Kia ora everyone. So I'm going to basically just jump right in and start telling you about some of kind of examples of how we're using machine learning and advanced tech in some of our earth science applications at SNZ. So starting with the example that Jess has already mentioned around hazard forecasting, and in particular flooding. So flooding is New Zealand's most frequent natural disaster and has massive impact, and there's becoming just more and more floods being forecast to happen over time. So there's a really high demand for kind of really accurate flood forecasts where we can start to actually predict in a real-time kind of flood response situation some actual impact-driven forecasts. So that's what we're starting to work on. So the first example I'm going to show you is focused on a town called Westport. So for the non-Kiwis, Westport is on the west coast of the South Island of New Zealand, effectively kind of over the hill from where we are now. It's the west coast of the South Island is famously very beautiful but very wet, and Westport in particular has flooded like multiple times over the last few years. So a couple of these events have been pretty massive. These images come from the July 2021 flood, where there was 800 houses evacuated and about 2,000 people affected. So on the back of all this, ESNZ kind of engaged with a whole lot of the stakeholders on the ground in Westport, including regional councils, emergency management groups, to support them in developing an operational flood forecasting tool. The goal being really focusing on trying to develop impact-driven forecasts. So many of you might know this, I guess, but basically when we're forecasting floods, this essentially involves a pipeline of physical models. So we start with our weather forecast. The weather forecast feeds into an ocean model, which will give us our storm surge, our wave setup, and our sea level at the coast. It also feeds into our national river flow forecasting tool, which gives the river flows of all the river networks around New Zealand. And what might happen in the case of an extreme weather event is that you might get a river flow in a particular area that reaches a particular threshold and will trigger some sort of warning that this area is at risk of flooding. So while this is great, this is often where in a kind of response situation, the flood warning effectively finishes. So we'll say, this area, the river flows are high, the area is at risk at flooding, but we can't tell you too much more than that. But the thing is, this is the map of Westport from bird's eye view. Flooding in Westport can happen through two flood mechanisms. So, for example, really strong storm surge at the coast can cause flooding through the Uriwaiati Lagoon, which is at the top right-hand corner, or via the Buller River, which is a massive river and can overtop and flood through that mechanism. Where exactly floods first and how this actually occurs is absolutely not obvious. It depends on the timing of each of these effects. And so basically, if you're on the ground or you're trying to make decisions about how to evacuate, it's absolutely not obvious what you might be needing to do based on river flows alone. So, of course, what we need is a flood map forecast. if we can do this, we can get the flood maps across the area. We can start doing things like feeding this through to, we have a riskscape software, which has databases of houses and floor levels and average human occupancies and things like that, and we can start making actual impact-driven forecasts. So this is kind of a picture of human safety threats, so it starts to identify areas that are particularly at risk for people and highlighting things like hospitals where you might need to evacuate first. So this is what we're working towards. The tricky part is, of course, that the physical models that you need to actually map from the river flow and sea level all the way through to flood maps require these hydrodynamical models that are really computationally demanding. So, in the case of Westport, we have this incoming weather event. The relevant inputs are the sea level and the river flow down the Buller. For the case of an area like Westport, this started off taking about 24 hours to run for a 5-day forecast of hourly flood maps. We optimised it a whole lot, and I didn't. A lot of the hydrodynamic models did optimise this a lot, and we got it down to about 10 hours, but it still becomes problematic for a real-time response sort of reaction. And I think somebody mentioned yesterday, the other thing that happens with this sort of thing is that it becomes really vulnerable to just human mistakes. You might put the input in wrong, and suddenly you have actually the wrong forecast, and 10 hours later, that's when you find out. So if I can go to the next slide. It does, however, make it a reasonably good candidate for a surrogate model. So through the course of this kind of developing this operational flood forecast with kind of, all these partners, we actually ended up developing this massive set of pre-computed flood events. So, this plot on the left here has each of these dots are a pre-computed flood scenario. The plot as the peak flow down the Buller relative to the peak sea level, and it kind of gives you an idea of the span of the flood events that we've simulated. But the actual variation in these floods is actually kind of more complicated than that. We looked at different timings of the flows relative to high tides. We looked at the different flood durations, so rivers that rise really quickly or more slowly. We also simulated kind of the design scenarios you typically use for planning, and also some historical events in there as well. So basically, through the course of this project, we built out this massive database. And we could train quite a simple CNN to then predict the hourly flood maps. So, training took a bit of memory. I'll say I didn't optimize any of this for efficiency. It was just optimized basically for accuracy. So, when I say it runs in 2 minutes, that's because I'm printing out absolutely everything under the sun. It's all very quick to run. And then we've got some accuracy comparisons relative to physics, physical models that show that it's basically as accurate as we need it to be. So in order to kind of demonstrate this capability, what we actually did was that we took the July 2021 flood event and we recreated the kind of forecasting capability we would have had back then if this surrogate model was available. So this is what it ends up looking like. So, this ran essentially under 2 minutes, and it gives us hourly flood forecasts for a 5-day forecast period. What I like about this movie is you can actually see how the flood comes in with the tide and then recedes, and then it comes back in and kind of overwhelms the town. And basically you can kind of see that, of course, this level of information would be really important for kind of allow the local authorities to be able to kind of respond and plan for incoming flood events. The other nice advantage of having a fast-to-run flood map forecast is that we can take advantage of these ensemble forecasts as well. So when we're doing our weather modelling, we use this ensemble technique where basically we generate 18 different members, which each have very slight variations in their starting conditions based on soil moisture and all sorts of things like that. And it basically accounts for the kind of uncertainty in this forecast and allows us to give probabilistic forecasts. So what we can do is we feed this through to get a probabilistic river flow, and then eventually through to the flood maps, and we can end up with an extra layer of information which gives the probability of flooding at each area as well. So that's just that kind of extra level of information for decision makers. This is an operational tool that has been used for kind of real floods in Westport, but I'll say kind of at the back of the conversation this morning, it's used alongside an interpolation techniques that the physicists have developed alongside this as well. So this was very much developed, in collaboration with hydrodynamical modelers, and they have these kind of interpolation techniques which are really useful, but they only give the maximum flood depths, like one snapshot. So basically what we can do is we can kind of make that comparison and feel confident that the time evolving machine learning is still giving us kind of an accurate representation. It also works well because we have a huge training data set for this particular location. So the question is, the master plan is, can we do this for the rest of New Zealand? This is obviously a pretty big step from kind of one region to New Zealand, but the golden gooses here is that can we have any incoming storm, one machine learning model that can run really quickly, and we say, okay, we have a whole lot of these vulnerable regions. What is the flood map looking like for each of these places? And this is how we're going to end up having a real-time impact-driven warning systems. For example, particular neighbourhoods are at risk of flooding. Please consider evacuating, etc. So this is actually, this kind of progression is reasonably good timing because ESNZ has just recently published a big database of national flood maps using our kind of design scenarios that are typically used for kind of planning and long-term risk analysis. So this is just a video of me navigating through the online database where you can actually look at the 100-year return period for Christchurch. So this is the flood map for kind of that 100-year return period then. This is, it's kind of limited. It's these one set of design scenarios, but it still covers almost the entire New Zealand. And so it actually does create quite a nice, at least proof of concept test set for me to start playing with. So there's a lot of work to be done here, but basically I'll just give you an idea of kind of where we're at in terms of starting point. So, on the what I've done is I've actually just taken these flood maps and I've chunked them down into this nice test set of just these 256 by 256 grids. And we have these two elements to it. One of them is basically what I very scientifically call water coming in, which instead of the kind of sea levels and river flows, I've just created these boundary conditions of flows around edge cells. And then we have our rain evolving over time up to our time step of interest. But of course, in order to be able to move a machine learning model around New Zealand, we now have to give it some extra information about the underlying kind of location and terrain. So we can give it some information about elevation, slope, and we're just playing around with some kind of early models, but we're finding that if you can map this using a Y-net, where the two different elements are encoded separately, mixed together and decoded into a flood map, it can do a reasonably good job. So this is very early stages, but it's kind of starting to, what I will say is put the water roughly in the right place. This is, very much the first step, proof of concept. And so we've got a few different avenues kind of where this might go next. We've got a project where we're looking at using a really efficient, low-resolution hydrodynamic model where you kind of simulate the physics using the low-res, and then we train a machine learning model to basically upsample to the high-resolution flood map. We have a whole big data set, and that's kind of a work in progress. We've also got a couple of options of starting to look at kind of some remote sensing incorporation into these sort of models as well, not to mention just actually having to figure out a way to generate flood scenarios outside these sorts of design events. But it's still promising. It's a first step, and we're hoping that we'll kind of keep progressing as we go. So I'm actually going to kind of leave the flood forecasting topic there and swing around to a slightly new area, which is where we're starting to look a little bit further down the track as to how some of these more emerging technologies might be used for earth science, which brings us to our quantum computing investigation. So just in the last few months, we're starting to basically investigate where quantum computing might have potential to help earth science applications. So this is obviously not an easy task, and one way of we're kind of thinking about this is that if you were to consider just one of these earth science modelling pipelines, for example the weather forecasting pipeline, the tricky part about about assessing quantum potential is that you have a look at this pipeline, and the reality is that in all likelihood we're probably going to have to rethink this entire pipeline, which I have demonstrated this is what it might look like. And of course, at the same time, this pipeline's already been shaken up by some of the AI, and so how all of these things merge together and what potential we might be able to get from quantum computing is absolutely not obvious from the outset. So our feeling was that in order to be able to start getting an understanding and a grip on some of these things, we kind of really need to get our hands dirty and actually start trying it out ourselves. So that's what we're doing, and I guess I'll say I'm not going to get into the kind of details of all the specifics. We're really looking at kind of existing packages and algorithms and finding out what they can do. Happy to discuss that stuff in the break, but I just wanted to give you an idea of the approach we're taking, kind of in the hope that that's of interest to this audience. So what we're doing at the moment is we've taken 2 kind of case studies to start investigating. So one of them being quantum chemistry for atmospheric applications. So that's, of course, of interest to ESNZ. And the other one being optimization for data assimilation, which is a really big one with a lot of potential, but a bit more of a question mark around the kind of quantum computing space. And what we're really trying to do is, I guess what we're doing kind of is developing a bit of a sovereign capability in this kind of earth science quantum computing application space. And we're trying to kind of have a look at these sort of case studies and use them as a way to answer the question, what are the technical barriers to actually implementing some of this stuff? What is the cost involved? And where is it at in terms of what it can do? And then can we project this forward as to how it might look down the track as the hardware evolves? And as I say, just start building up this capability in these areas. So when it comes to the quantum computing for quantum chemistry, this has been a fun one for me because this is my PhD area that I've managed to get back into and kind of crack open my thesis once again. So we've been running some, simple ozone simulations using kind of quantum computing simulators and just comparing these to the classical counterparts, getting a handle on what the difference in computational cost is, what the difference in cost is, doing some quick calculations how much it might actually cost to run one of these things on a machine, and then also looking at the scaling and kind of, if we actually wanted to start doing these things using quantum computing, so simulating reaction barriers for the atmospheric chemistry molecules we're interested in, what would that involve and what's the cost and kind of technical barriers to doing so. And then similarly, we've been looking kind of at, like I say, the one which has had a little bit more of a question mark over it for us, but was an interesting investigation. And this is around the idea of quantum computing for data assimilation. So I think we talked about it earlier. This data assimilation is the idea of incorporating the observational data into our forecast to improve the starting conditions and accuracy of the forecast. This is typically done using an algorithm called 40VAR, which is classically very computationally demanding. So in order to kind of play with this, we've been looking at the Lorentz 63 model, which is, just this simplified model of the atmospheric chaos. And basically, we've kind of just gone through the exercise of proving to ourselves that this kind of theoretically could be done. So we've formulated the problem in a way that you can represent it as a QUBO and then solve it using a QAOA quantum computing algorithm. And we said, okay, cool, you can do this. The next question being, do you want to? And the answer we kind of are finding is that using that particular approach, the answer is probably no. We have these toy models, and once you started to look at all the various things that would need to happen to make this look like a realistic system, it was unlikely to be computationally beneficial to do that. But we kind of needed to prove that to ourselves, and the whole exercise of going through this has been, I'd say, team bonding and also really, really educational and informative. And what we kind of get out of this is say, okay, well, maybe that approach didn't actually work, but we can now start to see the sort of characteristics of these sorts of problems which might work, and we've kind of got a few other ideas to kind of explore going forward. I think that's most of what I have to say, so all that leaves me is to say thank you very much, and drag Jess back up here for questions.